I'm Cristiana, and I will show you some of the results that I've been doing on generative AI, and especially applied to echocardiography. And I'll show you as well some of the current projects that we are working on at GE Healthcare using these generative AI techniques to generate images, mainly cardiovascular ultrasound images. So, yeah. I will focus first on giving you what's the challenge that we are trying to tackle here, and then I'll guide you through how we approached the problem and how we found the solutions and why we did the things that we are doing at the moment. So in echocardiography, in this imaging modality, there's a lot of variability in terms of the type of images that we can find in clinical practice. There is a lot of variables that can influence the variability of these data sets, and they can be inherent to the ultrasound modality itself. So the speckle patterns that you see, the ultrasound cone shape, so the area that's being imaged. Also, it's dependent on which type of scanner we are using to acquire the images, not only within the same vendor, because they can be different models, but also across vendors. So it's very difficult to get a data set which is consistent, because there is these variables associated with it. And then also we are trying to image an organ which is moving, the heart, and we can see it from different viewpoints. We can see more or less chambers in those images. So from 3 to 5, we can see different structures in one echocardiography image. We can put the probe outside of the body or inside, so when it goes through the esophagus. So the way you see the heart, it's different. The spatial location is different. And then, as I said, the heart is moving, so it is beating. So there is a cardiac cycle where the heart looks very different in between the moving stages. And then there is 2D imaging and 3D imaging. And inside the 3D imaging, there is spatial versus temporal. So it can be, the third dimension can be time, but time can also be a fourth dimension. So all these add to the problem of having curated data sets that reflect the variability that is present on the society. So it's difficult to create AI models that work well across cardiovascular ultrasound modality, because there is a lot of variability. And then there's also, of course, pathologies which affect the anatomy of the heart in a very specific way, adding more variability to these data sets. And then it's also dependent on the user, because different sonographers, cardiologists place the probe in different places, even though there's guidelines. So all these sources of variability, this affects the problem that is well established today, which is there is no public data set of ultrasound images. There is one or two, mainly, which are being used since many years ago, at least 10 years ago, but those data sets are small and they are limited. And comparing to other imaging modalities, ultrasound, like the percentage of ultrasound images which are publicly accessible is very, very low. So we're fighting this problem. Let's generate our own data, because even for us at GE Healthcare, we need to deal with the privacy regulations, and it's not always that easy to access new data. So we decided to explore the potential of generative AI to create such type of images. So we started by using GANs like 3-4 years ago, and we decided to explore the potentiality to generate 3D echo images. And this 3D, it's 3 spatial dimensions. So we are generating a heart, volume, which is rotated around the long axis. So all the frames that we are generating are actually like we rotate the probe around the long axis of the heart. So we train 3D GAN with that, using real 3D echo images and labels from a clinician. And after that, we created a synthetic data set where we used cardiac models from CT. So we used those 3D models to extract the anatomical labels from it, and then we generated synthetic images. And then to evaluate the actual potential of these synthetic images, we trained a 3D segmentation model using these synthetic images together with some real 3D images, and then we tested it on real data. And the results showed, first of all, after training the GAN, GANs have this problem of mode collapse, which is very common to happen. It means that the network just learns how to generate one image that yields a very low loss and keeps generating that image over and over again. So there is not variability in the types of images that the model generates. So we had to account for that. And after we accounted for that, we saw that the images that were being synthesized still need some kind of post-processing operations, mainly regarding the cone shape. For example, you see here at the bottom, we had to remove some extra areas which were sampled for some reason by the model. So we had to perform this post-processing operation to give the cone a certain shape. And also we had to denoise it because the speckles were not realistic on the synthetic image, but after we performed some denoising operation, which is very common in ultrasound imaging when we're trying to improve the quality of the ultrasound images. This wavelet denoising is a very common operation, so we went with it, and the image quality actually improved. So after doing the post-processing, we were able to generate as many synthetic volumes as we would want. So we generated a bunch of synthetic images out of anatomical labels of the heart, like these ones you see here at the bottom, where these three structures were the main ones that we were considering. So the left atrium, left ventricle, and the myocardium. And we generated a corresponding 3D image. Then we used it to train a 3D segmentation model, and we tested it on real data. And the results showed us that if we include synthetic data, synthetic images during training together with real images, then the segmentation on the test set improves. So it's closer to what the ground truth is. So led by this good result, there is potential of generating synthetic images and use it to further develop other AI models. In this case, we developed 3D segmentation, but we thought maybe we can still generate images, but use it for other purposes. And in the end, a couple of years ago, this was 2 years ago, yeah, I came across with the diffusion models, and I saw that they were never applied to ultrasound imaging, especially echocardiography imaging. So I went with this approach of using an adversarial diffusion model and generate 2D synthetic images of the heart. So the framework that I used here, it's not a simple diffusion model. The peculiarity in this case is that it's an adversarial one. This means that the network that is used to learn the reverse process, so the network that is meant to actually denoise the image and recover the initial training image, it's a GAN. And GANs can be conditional, so they can be trained in a conditional fashion. And that's what I did here. I used the GAN to learn the reverse process, so to learn how to generate a synthetic image, but I used a condition as well. And in this case, the condition was the anatomical mask. So I was making sure that the model was generating me synthetic echo image, but following the anatomical information present on the anatomical mask that was serving as a guide. And then instead of training another segmentation model, I performed some domain translation operations. So we could see that this model, we could prove its generalization power, so to say. So it can take any, can generate the equivalent of any image to another imaging domain. So how does this adversarial diffusion model work? So it is similar to the diffusion models. It's a two-path model, forward process, reverse process. So the forward process just takes a training sample, adds noise during a certain number of steps, until all you have left, it's a noisy image. And this is why these models are called destructive models, because you destroy your input. And all you have in the end, it's a Gaussian noise image. So you know the statistical distribution of this noise data set. And then on the reverse path, we use a GAN in this adversarial method. And this GAN tries to learn the statistical distribution of the initial training data set. And in this case, the training data set that we used was the CAMUS data set, which is one of the two public data sets that has been out there for 10 years minimum. And there is this particularity of this data set that all the images in it were obtained with the GE95 scanner. So the image characteristics are quite representative of this GE scanner. And what we did, that okay, now we have a model that can generate images that look like they would be acquired with this specific scanner. So let's take images from different data sets and make the equivalent as if it would have been acquired with the GE95 scanner. And we saw, after performing this on 5 different data sets, we saw that these diffusion models have indeed a good generalization ability, as they are able to translate between an initial domain and bring it and generate a synthetic data set which has a certain characteristics. In this case, it's the CAMUS data set. So it is capable of generating synthetic data sets whose images are actually similar to other images which would be acquired with the E95, for example. And these images also have into account the guide image, so the anatomical information. So we make sure that we can generate synthetic data sets together with anatomical labels, which in the medical field is also one of the things that we need the most to develop the AI methods. We need annotations, and it's very difficult to get them from clinicians. And this method of being able to generate synthetic images that already have labels was also another strong point in favor of using adversarial diffusion models. We calculated some metrics, mostly the PSNR, and it showed that the image quality was good. It's in the range of what's considered good quality image. And we also calculate the fit score. So the fit score, basically, instead of looking at each image at a time, it looks at the whole synthetic data set and compares it with the initial one, so before the domain translation operation. And we saw that, for example, the VQ-GAN Air dataset that you see here, it was the dataset with the highest fit score, meaning that it was the dataset which was more different from the CAMUS dataset. And you can see, for example, this is one example of one image belonging to this VQ-GAN Air dataset, and it's very different from what we were expecting to see in the CAMUS dataset. And after doing the domain translation, we saw that the largest difference it's actually on this VQ-GAN Air dataset, So the diffusion model was able to take a data set very different from what we are actually trying to generate, and was still able to generate images which fall within that statistical group that represents the CAMOS dataset. And here you have some examples of some images that we generated, some domain translation operations that we did to prove the generalization ability of the model. And then we were like, these were very good results. So we decided, okay, let's put this to 3D. Since we started with the VQ-GAN, let's generate 3D images, but using these diffusion models. But this time we decided to go even a bit further, and instead of using anatomical labels to guide the image generation process, we decided to focus on something else different now, and that would be the image detail level. Because from GANs to diffusion models, we saw that GANs have a lot more high quality. And then we decided to explore how far can we go when it comes to the image quality. So we use the VQ-GAN together with the diffusion model. What the VQ-GAN does is that this vector quantized generative model. So there's a generator, there's a discriminator, and the generator creates the latent space from the training data set. And then what we do is that we create this codebook, and this codebook can be seen, for example, as a dictionary. So imagine you have a dictionary and you say that you want it to have 1,000 words. And then you go to the latent space and you map each of the features present in the latent space to those 1,000 words on the codebook. But let's say that we want a codebook with 10,000 words. So you go to the latent space afterwards, and then out of those 1,000 features, you discretize them in order to make it match to 10,000 values on the codebook. So this discretization of the latent space representation, this is what makes the codebook. And this means that the larger the codebook is, the more detailed the image that we are trying to generate will be, because there will be more matches in between what the generator learned, extracted from the image, and what it's possible to generate. So with this codebook, with this very detailed codebook, what we do is then for the reverse diffusion model, instead of having as input the Gaussian noise latent space, we start from the codebook. So we have this quantized latent space, and we train in this case was a regular CNN to generate a 3D image of the heart. And then again, 3D, it's 3 spatial dimensions, not 2D plus time. And then as a Turing test, and to make it different from the rest of the work that we have been doing so far, we created this Turing test where we asked 2 cardiologists and 2 sonographers to evaluate some synthetic images in terms of different parameters, so we could assess the quality of these synthetic images. Before showing you those results, here you can see that there is a great difference between generating an image with a GAN and with this diffusion model. The detail level with the 3D diffusion is really high comparing to the GAN model. We were expecting it, but honestly, I was not expecting it to be this good. Because 3D ultrasound acquisition, it's very peculiar. So it was tricky. My computer is lagging, I'm so sorry. Here at the bottom, you see some examples of those rotations. And I'm not gonna ask you guys to tell me what's real and what's fake, but you can have an idea of what the model can actually do. And this is what the clinical users were presented with for the Turing test. So they saw a lot of these GIFs, and they had to evaluate it accordingly to 3 parameters. So image realism, frame consistency, and anatomical correctness. And before I explain further the graphs, the users were shown a real data set first, but they didn't know it was a real data set. We just showed them a bunch of real images. and asked them to evaluate accordingly to the image realism and all these parameters. And just so you know, they were not able to tell that all those images were real. They failed, and still looking at real images, they couldn't tell the images were real. So having that as a baseline, then we show them the synthetic images, the synthetic data sets, and these are the results. So the worst case never happens on any parameter. So like the synthetic image is never that bad. So, but in terms of image realism, what the graph is saying is that all of the users consider that more than 90% of the synthetic data set that we showed was realistic. So they were not able to tell which images were fake and which ones were real. And then in terms of frame consistency, they said that the majority of the images were consistent, meaning that there were no random speckle patterns in between consecutive frames. This speckle pattern consistency is really important in ultrasound because you cannot have, even though the speckles are random and they are associated with the patient, they have to be consistent throughout the whole cycle. It cannot be just random noise generating the speckles. And then regarding the anatomical correctness, all of the users, the cardiologists and the sonographers, said that at least half of the synthetic images had no inconsistency whatsoever. And one of the sonographers, which is the most experienced user of all these four, said that the synthetic images were totally anatomically correct. So she saw no incorrectnesses in the synthetic data. So this gave us a lot of motivation to, okay, we proved that generative AI has a lot of power to generate ultrasound images. So let's have some projects where we can actually use this. And that's my current role at GE. I'm involved in several projects where I use these diffusion models to generate different types of data. I'll talk a bit about two of them. Mostly, this is the main one. And what we're trying to do here is, like I said in the beginning, there are normal people, like normal conditions, so no pathologies, healthy hearts. But then there is also a lot of the population has abnormal hearts. So it can either be a small ventricle or a thick myocardium or a pointy apex, as you see here at the top. So all these characteristics, which are linked to pathologies, even though the pathologies are common, like the combination of all these characteristics in one pathology is not very common. So what happens is that the current AI models that are out there fail when they face there is such a patient, and then the current AI algorithms which are in the market, there is not enough of these pathological cases that were used to train those models. So they obviously fail when it comes to segment the ventricle, for example, in these pathological cases that show up. So what I'm doing is I'm using the adversarial diffusion model that I presented, and I'm generating these pathological images to use them to fine-tune the segmentation algorithms. So what we do is we use anatomical labels of the ventricle, which were delineated by a cardiologist, and they have the peculiarity of having been delineated on contrast ultrasound images, because the contrast ultrasound gives a lot more anatomical detail, so it's easier for the cardiologist to draw these contours on such type of image instead of doing it on a regular B-mode like this. So I'm taking the anatomical labels which were drawn by the cardiologists, and I overlap them with the B-modes, and I train a diffusion model to generate me synthetic abnormal images which follow these anatomical labels. And you can see that the label for the left ventricle, it's not what we see in current practice. I don't know how familiar you are with cardiac segmentation, but this is not how a ventricle is supposed to look like, to put it mildly. So then we generate this synthetic data set of pathological cases, and we fine-tune our segmentation model. So the segmentation model was pre-trained on healthy subjects, so people with no known cardiac conditions. And then we fine-tune it with real abnormal images. So this way we can create a benchmark. And after this, we started adding different amounts of synthetic data. So we can assess the impact that adding synthetic data has to this segmentation task. It's a current work in progress, but I can show you some of the results of the benchmarked model. So when we took the initially trained model and then added some real images with abnormalities and tested it on a real case, we saw there was a massive improve in terms of the DICE score for the segmentation of the left ventricle, which is exactly what we wanted to see. Like, we were working towards this goal to improve the segmentation of mainly the left ventricle. And we saw that it works for both different views and different time instants of the cardiac cycle. Here you have a different view and a different time instant where the ventricle is different. So at this stage, for example, the ventricle is larger than the ES. And you see that just adding real pathological images improve the segmentation model. And from now on, we will add synthetic data to it and see how much it will improve how further can the DICE score be improved by adding the synthetic data. It's a work in progress, so I don't have much to show right now about this, but we have high hopes that this is gonna increase the segmentation. As I showed in the beginning of the presentation, adding synthetic data to the training data sets improves the final segmentation. Another project where I've been using this 2D adversarial diffusion model, it's this Graph convolutional neural networks approach to perform view recognition on echocardiography images. And yeah, you might have recognized the author of this nice work, Sarina. So I've been working with her and together with other people at UIO and at VE. And she submitted the paper to the abstract to the MICAI conference last year. It was accepted for the ASMUS workshop dedicated to ultrasound imaging. And my part in this project specifically, it's basically, yeah, just generate more data for Serena. So I'm generating 2D frames of synthetic echo images, and a lot of different views are included. And in this case, so far I've shown you the condition was always just the left ventricle or the left ventricle and two other structures like the left atrium and the myocardium. And in this project with Serena, we are using a lot more constraints on the conditioning. So we are generating not only these three structures, but sometimes also the right side of the heart, also a bit of the beginning of the aortic valve, the ultrasound cone. So we are adding different complexity layers to this, and the results seem promising. So this is the other project where I'm involved in using the generative AI models on echocardiography. If you guys have more questions about this one, please ask Serena, she's the one, and you know how it is going. And that is it from me. Thank you for the attention, and happy to answer any questions you have.